Okay. First, two things that everybody's worried about at this point is your grades. I don't have the test corrected yet. I'll have them I'll have them done by Thursday. First thing, all the modules are now open in Alex, so you can go back and work on them all. This is how I'm going to grab your modules, so you can easily see what your grade is going to be for the modules. The prereqs doesn't count. I'm not putting that one in there. 2, 3, 4, and 5, whatever the percent is here, the day after the final, so basically at midnight after your final on December 9th, those are the grades that I put in the grade book. Okay, so you have until midnight on November or December 9th, which is the day of the final exam, to finish your PI. Okay, does that make sense? Awesome. So those are the grades that are going to go in there. Simple, easy to find. The final is December 9th. Yeah. You just get here by going to reports and click on your current module. It'll say full, and it'll show you all these, so you can easily see this on your side. Now, the second thing, because everybody always asks, oh, I hit the wrong button, but that's fine. I don't necessarily do extra credit. So if you do poorly on a test, you do poorly on a test. However, what I do is two things. One, if you got a 90 on every one of your tests, you do not have to take the final exam. So that will take care of some of you. I will look at the grades after this is done. As long as you got a 90 or better on all 3 tests, you're exempt from the final exam. You do still have to do your modules, though. That will still count. I take the average of your 3 tests, and that's your grade for your final exam. If you got a really poor grade on your test, you do have to take the final exam. But I will replace your lowest test grade with your final exam score if it's better. So let's say you get a 60 on a test, and you get a 75 on the final. I will replace your lowest test grade, that 60, with the 75 from your final exam. Okay, so you can use your final exam basically as an addition to a test grade. All right. I will never do the other direction. So if you get lower on a test on the final exam, I'm not going to replace it with another test. So you won't be able to lower your grade. You can only improve your grade by doing it that way. So those two typically take care of most of the issues that, like, I know sometimes you have a poor day with a test or whatever else, and it's like that takes care of those little issues. Any questions with either of those? All right, so your final exam is cumulative. Okay, so it will include everything. It will be a little more probably with what we're going to be doing now, just because this stuff hasn't been on a test, but it will be cumulative. You'll be doing derivatives. You're going to do some more of the application. So it's probably, since chapter 4 really used all of chapter 3 anyway, it's probably going to be more of chapter 4 and 5 on the test than the stuff in chapter 3, just because you needed the chapter 3 stuff to do 4 and 5 anyway. So in that respect, but there will be probably a couple problems on there just saying, just find me a derivative. Any other questions with that? So your final exam is on the 9th. It starts at 5:30, and I think it goes to like 8 something. It's a really long night, I know. Yes.
Curiosity. How would you go about doing that?
So when you go in, actually, I can say that. That was a good question. So when you go into Learn, if you click the little arrow, it drops down all your topics. Click where it says Chapter 5, and you can go back to any of the chapters you want. So that'll show you the Chapter 2 ones. That'll show you the Chapter 3 ones. So you can go back and say, okay, I want to work on this chapter, and fill them in. It's also a great way to study for your final exam. So if for some reason you did amazing, I haven't looked, and you finished all of Alex right now, and you want to go back and review, you can. If you click Review, this will show you every single topic that you have already done. So you can go back to review and go back and review those topics as well. They are also still there. All right. Any other questions? Okay. Let's prep you for Calc 2. All right. Find me the derivative of those 3 things. You should be able to get all 3. All three of these should be pretty simple to do. All right, let's start from the bottom and go up. What's the derivative of ln of x? 1 over x. What's the derivative of negative cosine of x? Sine x. What's the derivative of 1/3 x to the third? X squared. Good. Simple, straightforward. What we're doing tonight is going backwards. So what's known as the antiderivative takes that and goes back to what f of x is. Okay. So antiderivative, just because it's the opposite, the inverse or the reciprocal, or sorry, the inverse function of it, it is also known as an integral. That's the typical name you're going to hear from it. You're rarely ever going to hear antiderivative after this class. It's always going to be called the integral of it. So we need to be able to go backwards. So if we look at this, we figured out if you went this direction, this was 1/3 x to the third, right? What happens if I did that? What's the derivative of that? It's still that, right? If I did it's still that, right? Doesn't matter. So one of the big things is when we're taking the derivative, we actually lose information. We lose the constants at the end. So to take care of that problem, when you're taking the integral or the antiderivative of a function to go back this way, you have to add something. We have to say plus c. That is your constant term because we do not know. It could be technically any of those values. All right, so we have to put the plus c there to take care of that problem that we're losing that constant. We do get information in some situations to actually figure out exactly what those numbers are, but not always. All right. So this was the other one we did. So the antiderivative of, or sine of x is negative cosine of x. So if you remember your derivatives, you had sine of x, went to cosine of x, went to negative sine of x, went to negative cosine of x, and then repeated, correct? So the integral, so that right there is the symbol for an antiderivative or an integral. it goes the other direction. So that's why sine of x becomes negative cosine of x. This is actually important in this respect, and I'm not. It's technically it's still plus c, but this one's actually really important to put the absolute value symbol there, because I cannot have the ln of a negative number. However, in 1 over x, those values are in that domain. So if I start off with the derivative of f of x is 1 over x, I have negative values in the domain. So by putting the absolute value around the x and the ln, I take care of that problem. Okay? So the absolute value is important when you're doing the ln of x from 1 over x. When we were going the other direction, we were finding the derivative of ln of x, you already had that. So if they didn't have the absolute value there, that's fine, because that would mean my domain x has to be greater than 0. So you put those restrictions in place. So it depends on what the original function is. Since we're going backwards, we have to make sure we accompany for everything in that problem included in the domain. So let's look at the first problem. So how do you think we're going to do this one? How would we go from x squared to 1/3 x to the third? So we're taking this to get to 3. We're doing it plus 1, right? So x to the 2 plus 1. That's the x to the third. That number right there is the same number that's down there. So if it did 1 over 2 plus 1, it'd be 1 over 3. So if I don't know that, if I had x to the n, we would replace the 2's with n. So I have x to the n plus 1 over n plus 1. So when you're doing the derivative, we bring the exponent down and then we subtract 1. However, when we're doing the integral, you add 1 to the exponent and then you divide by that number. And that is the integral power law. These are the basic ones. We'll do a lot more of them, but these are the basic ones. If it's just constant times something, the same rule for derivatives, we can just ignore the constant, deal with the variable piece of it, and then multiply back by the constant to begin with. We can still split up addition and subtraction. We have, this one is your, that one right there is our power rule. The only one where that does not work is when x is or n is -1. If n was -1, what do you have? You have x to the negative first power, which is really what? What's x to the negative first power? 1 over x. And we have a special term for 1 over x. Because if you were to add 1 to that, we would get what? 0. And we can't divide by 0. So the 1 over x1 turns into the absolute value, or ln of the absolute value of x. E to the x is still e to the x. The sines and cosines still switch. There's my b to the x1. Tangent. So the sec is you take that one and it goes to the tangent. That's the opposite. Normally tangent goes to secant squared of x. The integral of secant squared of x goes to tangent. Same thing with secant x and tangent x. And then these are your inverse functions of sine and cosine. These two here, those are the hyperbolic ones. Not overly important. You're not going to see those too often. So I wouldn't overly worry about those. All right. This one looks really, really complicated. It goes back to what we were talking about with the derivatives. See, how can we split it up? How can we change things? So the 4 sine x is straightforward, but it's that fraction that's really going to mess you around, right? So what can we do with that fraction to make my life easier? I can, but then I have multiplication instead of division. Probably could do either of those, but there's a lot easier way. So, okay. If I have 3 plus 4 over 2, that's the same thing as saying 3 over 2 plus 4 over 2, right? So this becomes that. So that's really x to the 1/2, right? So I could just bring it all up and just make that to the negative 1/2. Because I have 1/2 minus 1, right? It's funny, I got into a long conversation with somebody online yesterday about why we teach math. And he was arguing that it was worthless. It was just a checkbox that people actually just, you have to do it to graduate or get a degree or whatever else. I'm like, no, it's all about problem solving. That's the entire purpose of it. This is exactly why. This is not a procedure. You can't go, okay, I'm always going to do this, this, and this. It's not an algorithm. It's not a formula. It's, okay, I've got this. What do I do? That's the purpose of math. It's like, wife the other day goes, do you know how to fix, we had something leaking in the house. And I'm like, sure, I can figure it out. Because it's problem solving. It's like, it's just, I might not know anything specifically about plumbing, but I know stuff about electricity that I can apply to it. So it's like, figure those pieces out. That's problem solving. That's what math gives you. So it's just like these. How can you manipulate things to make your life easier? Because now I've got a really simple problem. Now we only have to do what's sine and a couple power rules. So what is the, I'm going to say integral because antiderivative does not stick in my head. What's the integral of 4 sine x? Yep, -4 cosine x. That's the one you're going to screw up the most. Because it's so simple in your head. It's sine goes to cosine for a derivative. You have to remember it goes backwards, so you have to add the negative sign there. It is really easy to forget that negative sign, though. All right, what about 2x to the 4th? So we're going to add 1, so that becomes 5, and we're going to divide by 5. All right, what about x to the -1/2? So we're going to add 1. I'll clean it up in a minute. You are correct, but I'm going to clean it up in a minute. And then we divide by the half. So -4 cosine x plus 2/5 x to the 5th minus 2 square root of x. Why? Right, but remember we add first. So -1/2 plus 1 gives me a positive 1/2. That's the other mistake you're going to make quite often. You're going to have a tendency, especially if it's the same one, like with the 1/2, you have a tendency to just pull it down and then add the 1. You have to add the 1 first and then pull it down. Okay. And then don't forget your plus c.
So C can be all the color.
Yeah. Yeah. Because technically, does it matter if I had 4 C or 3 C's? If I added them all together, it's still 1 C. It's still a constant. So do what do you mean?
To use the integral equation, how would you format that?
Oh, this is good. So we'll get to that. Let's actually do this. All right, so this one, they give me more information. So they give me f of 0 is 4 and f of 1 is 1. So what that information does is it allows me to start finding the constants. Okay. So, however, the first thing we need to do, because neither one of those is a derivative, we need to find our derivative, our original function for this. So we've got f double prime, which means I have to do what to get back to f of x? Correct. So the first one is going to be f prime. So what's 12, the integral of 12x squared? Yep. So we get 12x to the third over 3, which is 4x to the third. 6x? This is another one that's really easy to screw up. What's the exponent of x? 1. So we add 1 to 1, we get 2. So 6x squared over 2, which is 3x squared. What about the negative 4? Yes. Exactly. Because remember, when we had just an x, we'd get rid of it, right? So in essence, that x becomes x to the 0 power. So 0 plus 1 is now 1. So we have x to the first power. We divide it by 1, which you don't need to write down. Plus, now, remember we were asking, does it matter if I have multiple c's for all the different terms? And I said no. It does matter in terms of when you're finding the derivative of that again. You do have to have the c there. Don't wait until you're done with the whole thing. And you'll see why in a second. So now, let's do f of x. So what's the derivative of 4x to the third? Or the integral of 4x to the third? Yep. 3x squared. X to the third. Negative 4x squared. C. Cx. That's y. Plus b. Don't use c again. We already have a c. Don't use c again. Now, they gave me information. They said when f of 0, when x is 0, the answer is 4. So f of 0 is 4. We can use these to find c and d. So since we have initial conditions, we can use them to figure out the exact value of the function at the beginning. So if I plug in 0, to all the x's, That means D equals what? D is 4. So now I have and then I have f of 1 equals 1. So I can plug that in. So 1 equals 1, 2, minus 2 is 0. So C equals negative 3. So my original problem is that.
Fourth step was methods to find C, or but there's 7 methods. Complicated. This is like when the term 0 want to use, you could use those in this specific function because it had 3 of x.
So yes and no. If for some reason you always need enough initial conditions to be able to find all the values. So since I had 2 variables, I need 2 initial conditions. The nice thing is one of them was 0, which made my life easy. If they weren't, I could have plugged them both in and used systems of equations to find C and D. And so just like if I was solving for 2 variables at that point. Which is possible depending on like if you're looking at like a real life situations are not always going to be clean. And if we're looking for those type of situations, it might be a little messier. And it was a little messier of an equation too. Yeah. Yeah, it's there's lots of little things that could happen with that. So the real reason, like we do some of this stuff, and we did some of this stuff before. Let's look at this one. Remember, we were looking for, or we had positions, we had velocity, we had acceleration, right? And we were typically you had one of them, and then you were able to find the other 2 based on that. Well, there's a lot of times where you're not necessarily going to know the position of the object because it changes constantly. However, you might know the velocity or you might know the acceleration, and you need to be able to figure out where it is in space. So in that situation, we have to, again, do the antiderivative or the integral to go backwards. So in this case, we have the acceleration function, which is 6t plus 4. And we need to figure out the position function for it. Now, this one, unlike the last one, because this is typical of something, you typically would know like the initial velocity because you know how fast it's going at the beginning. You might even know where it started. So those values they gave us our initial velocity and our initial displacement. We can use those to figure out our constants. So if we're starting off with my acceleration, what is the integral or the antiderivative of acceleration going to be? It's going to be my velocity. So it's 3t squared plus 4t plus c. Now, we do not have to wait until the end to do my C's and D's. I know this. I can use this. If I plug 0 in for all the t's, c is the only thing left. So this now becomes 3t squared plus 4t minus 6. And now we can find our position. We take the derivative of the velocity, or the integral of the velocity. So I have t to the third plus 2t squared minus 6t plus d. And again, now I have my initial condition there. So I can just replace the d with 9. And that's my initial displacement. All right. When does the ball hit the ground? All right. How many here is taking physics? What is a constant on Earth? What is acceleration? Yes, in feet. What is it in meters?
It's 9.8 meters.
Oh, it is? Oh, you're right. It is. I take that back. You're correct. It is 9.8 meters per second. I need it in feet for this problem because it's in feet. Anybody know it in feet? It's negative 32. Because we're going down. Sorry. For my acceleration, is negative 32. All right. You're right, it is 9.8 meters. Now you can find me my position. That's why you had that equation when you were in high school. It was always negative 16 t squared. That's where it came from. Okay. That's not what the question's asking. How do you figure out where it reaches its maximum height when it hits the ground? Okay.
Go back to D instead of 0.
Right. So this is one of those situations where you can sit there and find your vertex and everything else like it's because it's a parabola, but we have its derivative. Use it. And it's not asking me for the value, it's just asking me for what t is. So for maximum height, that's where v of t is 0. So t equals 48 over 32. Which is 1.5. So when does it hit the ground? How do we figure out when it hits the ground? Yeah, so this one we do have to do some stuff with quadratics. You could try to factor it, but you don't have to. Like in a problem like this, just do the quadratic formula. Now, I would simplify this problem before you did it, because otherwise the quadratic formula is going to be really messy. Can I divide them all by something? So try it. That's the easy one. You have a calculator, try it. It does. So then we have x equals 3 plus or minus 9 minus 4 times 1 times negative 27 is 108 or 118. Nope, 108. It's approximately 6.9 seconds. The negative one is going to be negative, so it's not going to help. It's going to be. I'm throwing the ball forward. Yeah, it's going to be outside. All right. So the entire. So we have integration. We have derivatives. Derivatives find us slope, finds us rate of change. We can do that for any function. Integration will take us back to our original function, which is helpful for certain things. The big thing that integration does, though, is it gives us the ability to find this area, which sounds weird that would be important. However, we can find, like in geometry class, you figured out you could find the area of a circle, you could find the area of a triangle, you could find the area of a square, you could find all those areas. So it's simple. How would you find the area under this? How'd you find the area under that curve there? So, and then the question is, well, why do we care? Why would it be important for us to find the area under there? Well, that ends up being what's known as a cumulative growth. So if I was to add up all the values underneath there as time goes on, I would get an actual value that could be useful. So we have simple things like compounding interest and stuff like that, those things. So it's basically a sum of all the values before that point. So finding area is kind of helpful for a lot of things. And we can use integration to do it. But before I actually show you that, we have to figure out why it works and where that wonderful symbol comes from. So if I asked you to find the area under this thing, how would you try to do it? Because you obviously don't know all the tricks yet. So if your geometry teacher asked you to do this, what would you try to do?
It is close to
How?
that thing. Or not that thing.
Okay. So you like that?
Yeah, but something more with it. But yes,
How would you get another straight line that's more within the blue?
just closer to the tangent.
To what tangent? But that see, this is the thing. At this point, there's no wrong answer. Like doing this actually would work. You could absolutely do this. We have one here and one here, right? So what's the area of the triangle? How do you find the area of a triangle? 1/2 base times height. So the area in this case would be 1/2. Okay. It's an approximation, but we have a lot of extra stuff out here, right? So it might not be the best approximation. All right. So not you, because you gave me an idea. Somebody else. How can we better approximate? Yeah. Okay. So I'm just going to make one because I just don't feel like doing a bunch like this. So do this one and then do this one. Okay. That would get better. Well, what kind of shapes do we have now? Okay, so now we're getting a little bit more complicated formulas, right? But this is good. What's an easier shape than a trapezoid? Square. So instead of doing a trapezoid, now obviously this would be a horrible one, but if I did it from there to there, and there to there, that'd give me two rectangles, right? Yes, this one's going to give me a lot of extra space. But now think about it. That's one, right? That's only cut it down to that. What if I broke it here and here? So now, getting closer. So that would be like, this is a lot better drawing than I did. I'd be like that. I also could do the other direction. So this is known, that would be a right. What do you think the right stands for? Not right angles. Right's where we're starting. So I'm starting at the rightmost point and going over. That's where those lines are coming from. This would be L4 because I'm starting at the left point and going over. So we get over to the next one. If I, instead of doing 4, if we did 8, now we're getting even closer, right? So what do you think we're doing here? Think back to what we did, some of the stuff we did at the very beginning. Mm-hmm. Okay, so if we look at the length of these, right? These were 1/4 times f of x, whatever the height was, right? And this would be 1/8 times whatever that height was. Because we're figuring it out each of the points. So those values are on the function, so that's that. So this piece right there keeps getting smaller and smaller to the point where we could end up doing it basically to the end. So if we kept shrinking that down and shrinking that down and shrinking that down, this ends up being like this. I'm purposely not making you do this because you're never going to have to do this. However, you do actually end up seeing this in your Alex ones in the module 5, chapter 5 stuff. So it's kind of nice to see. So remember what we were doing back here, right? I said it was 1/8 times f of x, and that x is whatever the values are. So it's 1/8, 1/4, 1/3, and so on and so forth. So it's one n, and the second one would be 2 n's, 3 n's, 4 n's, 5 n's, 6 n's, 7 n's, all the way up, right? So 1 n, 2 n, 3 n's, and so on and so forth. The function was x squared, so that's why those are squares. But we're going all the way out to n because we're going to infinity. So if I pulled out this, we get that. And these from these. So I have 1 over n to the third plus that big long thing all the way to n squared.
The number later. 2 and 3. zeros.
That one would be 1n, right?
Yeah.
That'd be 2 over n. So let's think back to let's think back to the eighths, right? That's 1/8, that's 2/8, that's 3/8, that's 4/8, 5/8, 6/8, 7/8, 8/8, right? So if we just did it to the ends, it'd be 1n, 1 over n, 2 over n, 3 over n, 4 over n, all the way to n over n, which is what I got. The end was the 8 over 8. It's 1. So we've gotten down to this, but we still have this mess right here. You're not expected to know this. There's a formula for it. Want to hear the crazy thing? The guy who invented this, who came up with this formula right here, did it when he was 11 years old. And did it because his teacher told him he couldn't do it. So the story was, so his name is Gauss, and he was told by his teacher was bored, and he was extremely smart. Like his parents were brilliant, right in mathematics and everything else before this point. So he really knew his math. So he got annoyed in class and he decided to torture his teacher. So the teacher told the entire class that they were sick of it. So the teacher told the entire class to add up all the numbers from 1 to 100. If I told you to add up all the numbers from 1 to 100, now remember, this was, well, I didn't tell you, this was in like the 1600s. You didn't have a calculator. So you'd have to add up all the numbers from 1 to 100 in your head. He came up with the answer in less than like 20 seconds. Told the teacher the answer. It's 5,050. So she told him to go outside and add up all the numbers from 1 to 1,000. He came back inside 30 seconds later and told her the answer. She kicked him out. He didn't go back to school after that one. His parents told him out. But that's how smart he was. Like, this was stuff that he literally invented the method to be able to add sequences of numbers. And this is another one of those ones that he had done. Add this sequence of sums. So if I had 1 squared plus 2 squared plus 3 squared, what do I get? Wherever n ends, this is the formula for it. It's n times n plus 1 times 2n plus 1 over 6. So now we have our formula, all in terms of n. So let's look at the limit as n goes to infinity of 1 over n to the third So can we clean this up? If I put this partially together, that n and that n will cancel out. I get 2. So I have n plus 1 over 2n plus 1 over 6n squared. All right, so how am I going to clean this up more? How do I find the limit of this? What's the method you know to find limits? Huh? So it's a limit, not a derivative. So critical numbers aren't going to help. I could do the Hopital's rule for this because you do get infinity over infinity. But do you really want to automatically go to a derivative to solve this? That's the bigger question. Remember, there's other ways that we can solve limits. Think back to the beginning. What was one of the methods that we used to solve limits? It's a great review for your final. Because there will be a couple limits on the problem. Yeah. Huh? It's actually already factored. We could FOIL it out, but that's not going to help me. There was a method we said we could divide things by things. Yeah. So remember the goal when we're looking at going to infinity, if I get it something 1 over something, 1 over x, that going to infinity goes to 0. That cancels things out. Makes my life easier. So if we divided everything by the denominator, the degree in the denominator, that will take care of a lot of things. So if I divide the bottom by x squared and the top by x squared, the one thing I'm going to do to the top is the piece that might be a little more complicated that when you think about it. I'm going to split this because I have 2 of them. So I have n plus 1 divided by n and 2n plus 1 divided by n. And that's 6n squared over n squared. Because if I multiplied those 2 n's together, what do I get? But these are multiplication, it's not addition. So when we have addition, you're right. I would divide them each by n squared. But when I have multiplication, if I go backwards, I still have to get back to something over n squared, right? So if I had 3 halves times 5 halves, right? I would get 15 over 4, not 15 over 2. So that right there is like saying 2 squared. 1, 2, 2 2s. If I was to break it back up. These are all the little algebra things that make your life easier when you remember how to do them. So n over n is 1 plus 1 over n, 2 plus 1 over n, over 6. So I have 2 over 6, which is 1/3. That you can always do.
By the X.
The degree on the bottom? Yeah. It doesn't always help you. That's the thing, is it doesn't always work. But you can always do it. So now this one, if you think about what we did a little bit ago, we already did this problem. So this symbol right here, it's an elongated S. Because what did I basically do up here? It was a summation. I'm adding all those things together. I'm adding all the rectangles together. So that elongated S basically means the summation of all those rectangles. That symbol, that right there, is my integral. Where the symbol came from. So the integral of x squared, and you'll see it written like this. So the dx is the change in x. That's the variable that you're integrating based on. So in this case, we're taking the derivative of x, or the change in x. We've done this one already, right? This one comes out to be what? 1/3 x to the third, right? Let's see. So this right there, this piece up here, this is an indefinite integral. Because it goes on forever. Did my area go on forever in this case? No, we're stopping at 1. We were only looking for that piece there. This is a definite integral. So if I took 1/3 x squared and I plugged in 0 and 1, I would get 1/3. So the integral does what all that limit and everything else I just did before was. What we did before was known as a Riemann sum. So it's the limit as n goes to infinity of the rectangles. The integral does that all for me, so you won't have to actually go through and do all that extra work, which is kind of nice. Which is why I said I'm showing it to you so you understand where the integral comes from, but we're not actually going to do any of it. All right. We'll do more definite integrals on Thursday. There's some more stuff I have to go through on it. But you can at least start doing 4-9 stuff in Alex. All right. Any questions?
It's the notation on the bottom.
This?
Yeah.
It's 1/3 x squared from 0 to 1. So it's telling it's from there to there. That's actually the stuff that I'm going to really go over on Thursday when I'm talking about the definite integrals. I'll go through with all that means and whatnot. The only reason I even showed you this is because I wanted to show you how the 1/3 came out as compared to what we were doing here. So that more leads into the next chapter, but I didn't just want to leave it here. I wanted to show you the connection between that and what we were doing before and why we started off with the x squared problem at the beginning. All right. I will see you on Thursday.